Ivy, let me tell you a few words about you.
Okay,
And
okay.
so, everybody, we starting our keynote, and it will be given by Philippe Kahn, who is a well-known mathematician, inventor, and scientist. Those of us who used Turbo Pascal, Turbo C, or Turbo C++, the best idea of that time, and other Borland products, they know well who Philippe Kahn is. And Philip kindly agreed to be our keynote speaker, and today he will share his vision of the modern software development and probably much more. Philip, take over.
Thank you. Good morning. My title, Bigger Models or Smarter Teams, uh, it looks like a contest. It's not. My argument is that um, um, neither one is wrong and neither one is right, and it's important to frame that choice. And we're going to be looking at through this talk to the architectures that for intelligence basically, and the future will use both, in my opinion. And we'll talk a little bit also of world models, which basically encompass both. Um, I learned the lesson kind of building the camera phone in back in 1997. The breakthrough was not a bigger phone or a bigger camera or a bigger network or a bigger whatever. It was the cooperation between systems that were not necessarily meant to work together that demonstrating something important, which is capability emerged from coordination. And that's to me a very important piece of what we're talking about. And so that tension is something that I was thinking would be good to explore today. A large central model gives us something coherent in context. An orchestrated system gives specialized components explicit roles, independent challenge, and accountability. Don't confuse an orchestrated system with a bunch of agents that interact with each other. We're going to talk about explicit roles and independent challenges and accountability. The real design question, I mean, when we're building something, uh, is not which architecture wins in the abstract, really, because that's kind of a theoretical thing, is where do we need coherence and where do we need independent judgment? And that's really a very important part of this. As you well know, it's all about making predictions, and the best wizards don't always make the best predictions. So I'm gonna stay concrete, and I will compare these architectures and look how the word functions kind of in that light. Um, so my second slide really is a very important slide. Is that we are not born unfinished. And that's really the very important part. This is not by defect. It's because the baby has to uh, pass through the birth canal, and so needs a flexibility in the skull, and the skull needs to be able to develop as the brain develops. Uh, and so the skull needs to an infant skull needs to accommodate a rapid brain growth afterwards. The broader point is that human intelligence does not arrive in a brain and it's there. In a complete model. It develops through feedback, imitation, correction, language, pain, culture. Intelligence is not only what sits inside one's brain, it's also what happens through regulated, and that's an important word here, regulated interactions and other people and with the world, regulated interactions with other people and with the world, and that's extremely important. So I'm not claiming here that models are children and that biology is the way to explain um, well, AI in many ways. Um, I always say that the most important part of intelligence, what I call organic intelligence, which is our own intelligence. However, um, it's important to look at our organic intelligence and understand, you know, what's the step? What's this? And a lot of people are thinking it's more power, but perhaps it's a little different than that. The useful analogy is narrower, is that the capability changes through interaction. A system can be corrected, challenged, and updated can become much more reliable than one that produces an answer from a fixed internal context. So you can see already that I'm actually contrasting the what I will call the God model with the orchestrated model in the way that they're both are important for different reasons. For decision system practitioners, this matters because um, we we evaluate the model while ignoring the architecture around it, and that's really important. That who proposes basically the who challenges, how the evidence is checked, and who is allowed to stop the process matters as much as the model itself. There's much more to it than the model, and that's really important. Uh, Maybe the the thing to remember is nature itself shipped our brain before finishing. It's the enclosure. It's like uh, nature gave us that brain before finishing the enclosure. It's maybe in the high tech version of an agile launch. If you're into agile software methodologies, so that gives us two legitimate architectures, really. And so my next slide is going to kind of not compare them. And this is not, I mean, this is really important. I'm not trying to compare. I'm just trying to look at the functionality on each side and see how we can choose and how we can select what we need for our own application. Uh, there's a real trade-off. Orchestration costs time, costs tokens, costs engineering effort, uh, operational complexity. More agents do not automatically mean more truth. In fact, poorly designed debate can amplify errors or create an expensive loop that never stops, a kind of an infinite loop. If you think about it, um, this orchestration is about, in many ways, create a creative, positive debate as opposed to accepting truth for what they are. Um, a practical decision rule, uh, when the cost of a wrong answer is modest and coherence is valuable, it's probably what I call the God model. I mean, and by the way, I'm calling it the God model. Don't think that I want to be respectful of everybody. It's just a good way to think about it. Uh, when a decision is consequential, multi-step, regulated, or must be explained later, then an orchestrated, independent, explicit authority is really important. And of course, there's always a hybrid path that is available. The same strong foundation model can play several roles, while external tools, rules, and differently trained models uh, can provide independence where it matters. So, you could use as an analogy, um, people sailing on a sailboat. If everybody tries to grab the wheel at the same time, there's no way you're going to go to where you're supposed to go. And so, there, the regulation, the regulatory, is the rule based approach is really important, and so orchestration can coordinate identical or different models, uh, and that's really an important piece. So this comparison table is not meant to show which is best or which is worse, but rather help in choice for an application, for example. So my next slide is going to start examining the God model. So the God of gods is Zeus, and this is a statue of Zeus. You can see, um, um, and so well, I've used Greek mythology actually as a as a metaphor because when the Greeks wanted to explain the world, they saw, an omnipotent God, but he wasn't the only one. But really, the Zeus was the god of gods, or at least the ones on Earth. Um, and and then they couldn't explain everything, and so they had to invent all these gods, all these spirits, all these. I think that explain thing, and that's more of the distributed model, and we'll talk about it as such. So the structural trade-off appears when um, generation and verification inherit the same assumptions. Um, if you ask a model to criticize itself uh, and improve the answer, it's much harder. And think about yourself. We can be critical of ourselves, but it's very different than if you ask a objective observer. And so the God model, creates his own guardrails, but in many ways is not as objective as an independent as an independent system. Uh, the same blind spot can survive both the proposal and the self-check, and that's really one of the challenges of the God model. So the centralized model is often, or God model is often there to be the correct default. I mean, if you don't want to think about things, and you'll use this, but um, use it when one coherent answer is the objective, when the action is reversible. Because if the action is not reversible, then it's much more difficult. Take for example a self-driving car. Um, Running into a tree is not reversible, um, um, as opposed to asking your system to build a budget for your company in a spreadsheet. That's reversible. And and when external verification adds more cost than value, then the God model is a good model. And um, we escalate to orchestration when the risk profile requires. It's not because a multi-agent diagram looks more sophisticated or cool or whatever it is. A multi-agent diagram is not, and I'll get to more details on that in my next slide, I guess, but it's not just a bunch of agents chatting with each other, because that doesn't do much. And we'll talk about how the interaction gets regulated and what orchestration really means. Um, so so it's clear that the God model is the most used model today, and the simplest to implement. You everybody can take ChatGPT or Gemini or one of those, and 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 build their own system pretty quickly. So let's talk now about the orchestrated model. So, as I said about the orchestrated model, um, uh, the Greeks created all these gods and spirits, etc., because that allowed them to explain what was going on, and they were all having arguments and fighting each other, or loving or hating each other, etc. And so um, you could argue that Zeus was fairly poor orchestrator, but that kind of mixed both models at the same time. So orchestration is not several agents chatting, and it is, and this is really important, it is regulated interaction. So the first role, if you look at that little diagram that I got there, is to propose. Then the second, call it agent if you want, is to challenge and look for failure modes and et cetera. Then the third one is to verify and test the evidence, and then apply the policy and get back to it in a closed loop and continue doing that. That is basically the regulated interaction. It's not just, everybody doing something and then at the end hoping that something uh, positive will come out. The roles must be independent. There has to be explicit dissent allowed. Uh, the handoffs must be regulated, and the decisions must be auditable. And that's really important um, because, as you know, especially in enterprise applications or real-time applications like, self-driving car or whatever it is, uh, we want to understand what happens so that we can, or the system itself can continue improving itself. And so that cycle is really critical with orchestration. That's a really important piece of the pie. So now that we have kind of a God model and an orchestrated model, um, what's a world model? I mean, you've heard from where my good friend Jan LeCun has been pushing that and telling people, all these LLMs are great, but think about the fact that um, that that first analogy I talked about um, is that you're not born with everything in the brain. What you are is a product of what you started with, but all the interactions with the world. and and basically it's the world, it's sensing, it's the model, and it's acting. And so it's the cycle of perceiving, simulating, and act and learn. And we learn in the world ourselves. Little kid touches something hot. Oh, it's hot. I burn myself. And then that. And so that's kind of a world model does not contain the material world. It contains a learned internal representation of how states evolve and how actions may change outcomes. So the physical loop itself starts, as you can see from this little diagram, from sensing. Sensors encode the current state imperfectly, like any sensor, uh, and with noise. The model simulates what may happen next. The controller chooses an action. That's a controller. Then an actuator or person, okay, executes it. The observed results returns as new evidence and feeds the loop. And the system continues learning like that. And that that final step is the key. Like reality supplies the error signal. And that's really um, that that's really essential. The gap between prediction and outcome corrects the next estimate or policy. A world model is therefore not just a richer chartbot; it's part of a control loop. And this is the important part. It's all a control loop. And of course, it embraces both the God model and the orchestrated model. Uh, but that's really what the key and so this is how intelligence is in general developed. So as an example, in a sleep environment, for example, that's something that in my company we work on. We place sensors under a mattress, and uh, With that, we estimate movement, heart rate, respiration, and sleep state. We also take environmental inputs such as temperature, um, uh, air quality, humidity, etc. Um, and the system predicts whether a small change, perhaps, to the temperature in the room or to the shape of the bed or whatever it is, will improve the state of the sleeper. And this works in a closed loop. So it's basically a simple world model that's focused on one thing, biosensing or sleep or something like that. So it acts within defined safety limits and then observes what actually happened. So for practitioners, uh, three disciplines follow. You have to keep the sense state separate from the model inferred state. Prefer small, reversible actions when uncertainty is high. Think about the think about the self-driving car, and never confuse a confidence simulation with evidence from the world. So, we always think about reality, and I'm running a PowerPoint here, uh, and it's a very simple slideshow. I just decided to only use 9 slides or something I got, and um, and if you think about it, reality is the only participant in this meeting that can't be persuaded by my beautiful PowerPoint. So reality is reality. I can convince a lot of people through my eloquence or lack of it, and but reality is reality, and that's something that we practitioners in this world think about. So uh, so I wanted to use a practical application um, for closed loop. And so this has to do with sleep. I mean, that the reason I'm not trying to, we don't sell anything. Actually, we're science-based technology company. We make technology basically. Um, and so what I wanted to give as an example of how we can change um, common misperceptions. If you listen to everybody who talks about sleep these days, you'll find that most people will tell you, "Oh, you just wake up when the sun shines, and you go to bed when within certain time, and when the sun sets, and you're all good, and you're fine, and everybody should have that schedule." Well, is that the best way to think about it? And you start thinking about how we eat, how we sleep, etc., and how all that has been very much influenced by the realities of the Industrial Revolution. When in the times of the Industrial Revolution, people wanted to send people and keep them in factories for mass production. Well, they decided that having breakfast at 6 a.m. was the best thing, getting into the factory at 8, working till 1 p.m., then getting a 30-minute break for food, then working another 5 hours or something like that, then back home, eating dinner and going to bed. So basically, that created that cycle, uh, both for food, I mean, for the way we eat, 3 square meals, so-called, and then the 8 hour mythical night of sleep. That's not how historically things happen. There was something very different, is that if you think about our 25,000-year-old Stone Age ancestors, um, some of them had to keep guard to make sure that the saber-toothed tiger wouldn't intrude and create massive damage in their cave, and others had to hunt at night in the moonlight, and there's all these different terminologies that were developed that way. In other words, there is not one way for people to eat. There's not one way for people to sleep. So we call that the circadian uh, the circadian cycle. And this is my next slide. And so um, fundamentally, there are larks and there are night owls, and there's a lot of people in between. All of them can be equally healthy, and all of them don't need to be put on the same schedule. And so when we started studying that from a machine learning perspective, a deep learning machine learning perspective, we actually took the input as you can see from the top on, cardiovascular input, respiratory input, um, activity input, movement input, then light input, and then environmental input. Each one of them has its own logic, is independent of the other, but together and this is a little bit of a simplification, but together they paint a picture of how you perform. And so what we call here the COA, COA stands for Knowledge Organizational Architecture, is the orchestrator. And the orchestrator looks at all that and basically compounds all of these, um, rather than centralize all of these in um, in in a single number that we call the circadian score, which centers your optimal time of day, your noon if you want, or midnight, whatever you call it. And it's different from all of us, and it evolves constantly because it evolves in a loop. So it's a combination of orchestration and a world model, and evolves in a loop. So we 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 looked at um, over 250 million nights of sleep, and used, of course, machine learning to actually understand that, and all the labeling that we needed to put together, and try to extrapolate something that we could call a circadian score that would be useful to your average human, who understands that although I have to be at work at 8, my ideal time to be at work should really be 10:30. And so hopefully over time, this becomes something that helps people live a healthier and better life. A lark, someone who wakes up with the sunrise, or a night owl, someone who works better at night. We know a lot of larks, lots of athletes, etc., and also lots of night owls. People like Einstein or Mozart were night owls, or Margaret Thatcher. Actually, she only slept 4 hours a night. Um, so we know a lot of we know a lot of them, and many of them can live a very healthy life, and that's a really important thing. So I'm using this as an illustration of the practical use um, of world models together with orchestration to give an actually a practical example. So I'd like to finish with a quote from one of my uh, very uh, favorite favorite scientists, and my favorite book in the world is the Origin of the Species from Darwin. I think that we can apply a lot of it here. Um, I'd like to remark first, this is kind of a clever remark, but a lot of people say that the species that survive are not the strongest and smartest, but the ones most responsive to change. Is Darwin. It's a paraphrase of Darwin. And so here, I want to be a verifier in the sense of what we talked about um, in terms of orchestration, and do justice to Leon Mangson in 1963 said that. Another version of Darwin's quote is that the species that survive are not the smartest or the strongest, but the ones that are most responsive to change. And I think that is so appropriate for this talk because fundamentally, um, what we're talking about is the responsiveness of the system and the ability the system to adapt to what it perceives as reality. And that's how I think the the powerful models, the specialist agent interaction, and the regulated agent interaction through orchestration are so important. So my conclusion is pretty simple. Um, Scale, centralize capability where it helps, distribute judgment where the consequences demand it, and make the interaction accountable. And so the centralized capability, distributed judgment, and that's really the key. The judgment, the self criticism of the system, it doesn't perform as distributed judgment. So that's kind of concludes my prepared remarks, and I'm happy if you have any questions to entertain questions.
Thank you, Philip. And we have a few questions in the chat, but I would ask people just unmute yourself and ask direct questions.
Jump on the bandwagon. Trevor Miles here. So around the orchestration side of things, well, let me step back. I'm firmly in Jan LeCun's camp. I use LLMs for narration, never for decisions, because I don't think they can sufficiently encapsulate the knowledge that's necessary in the system to make decisions. So I'd specialized neural nets to do that. But I was interested in the orchestration side of things. Your text didn't show it, but your voiceover seemed to indicate different parties making a decision on one particular value or one particular context. But I'm more interested, I come from supply chain, and I'm more interested in the decisions where an agent needs to make a decision that crosses boundaries of responsibility and needs to work with other agents in order to make that decision because they don't have the full responsibility for ticking the box or actually actioning a decision. The example would be of a person or an agent that is promising an order delivery time to an important customer, but there's not enough material. So in order to do that, they have to buy more material, but they're not responsible for buying the material. But even then, that material has to be expedited to get to the customer in time, and they don't have the responsibility to approve expedition. So, but nevertheless, they need to have 3 or 2 other agents work with them, one to buy the material, one to approve expedition, in order to arrive at a good business decision, which is to satisfy that customer's order on time. So would your orchestration cover that model as well?
Yeah, absolutely. I think what you're describing is more than just agents acting independently, but you want regulation because you don't want an agent, one of your agents, to go and order 2 million parts XYZ when you only need 20 parts QRT. Uh, so the orchestration model is very important in that respect because That's where the rules and the regulation go together, and has to work in a closed loop. So I would think that in such a system, that's even more important and applies directly.
Thank you.
More questions, please? Paul, Vincent, you had a question? Okay. Sarah, your question.
I was just curious in the world model, how does this account for, or whether or not it does account for overfitting or, yeah, just trying to have like a perfect estimate if the data that the sensors or the context starts with kind of suggests a trend that doesn't really actually match like the underlying principle or pattern of the world that it's observed in.
Yeah, I mean that is that exactly that's really the challenge, and this is why you want a closed loop system, a closed loop system in a world model. So it starts with the sensing, if you think about it, and the sensing is never perfect. Sensors need to be calibrated. The sensors are out of calibration, whether it's a LiDAR, a radar, a temperature sensor, a blood pressure sensor, whatever, blood glucose sensor, and for diabetes, stuff like that. All this, all, nothing is 100%, but what we have is we create a closed loop system with a regulated closed loop system with challenges and with challenges that actually validate things all the time. So a good example is a self-driving car. I mean, there are no perfect self-driving cars today. I mean, some of them with a lot of sensing run in San Francisco. Our Waymos in San Francisco, we've got a lot of those, and they work pretty well until they don't. And we've all seen the videos of them honking at each other and stuff like that, or people getting stuck in one. And it's a world in progress, just like a child is not born with their intelligence in their brain. Actually, the we started with that. The skull of the child is it's flexible enough that it can accommodate a growing brain. And through trial and experience, hurting, ended up in the hospital because they broke a bone. Now they've learned something, and I think the concept of world model is very similar. Not that we want to transfer, biology into science. It's not really a good analogy, but it's a metaphor. And so as far as metaphor is concerned, uh, the only way we can bring intelligence to system, real intelligence, is actually to follow a same idea that all intelligence cannot be built in a theoretical system. It has to be done through trial and error and through experimenting and working with the world, as long as we're trying to build more advanced systems. Example, we had two examples on this chat. And so I totally agree with you. It's absolutely the case that there are going to be errors and it's going to work or not work and all that. And the key is to design systems that will accept that. And and that's where self-criticism a lot of times doesn't work, and that you have to have critical agents and checks and balances and all that. And that's really very important. And in case of a human or a child, checks and balances are breaking a bone. You learn from that. But another example that you get from or early learning from kids. If you have a child in a high chair, you may have experienced that yourself. I know I have, and they're eating the delicious soup that you made or whatever it is, the puree of apples with mangoes, and suddenly they take the spoon and they throw it over the chair. And you go, you pick it up, you wash it, you give it back to them. And they do it again. And then they do it 7 times. And then you go, you go, stop doing that. And that is the big mistake that parents make, is because what the child is learning about is learning gravity. It says, oh, is it true that every time I'm going to do the same thing's going to happen? And he's experimenting, getting to learn the world. Why would we think that our clever systems, AI system, don't need to learn the world and don't need a process to do something like that? In my opinion, it's my opinion, it's very similar. There's going to be some silly things that appear, and there's going to be progress made, and it's a told and evolving process.
Okay, thank you. Philip, may I ask you a question to you as a developer of very complicated systems, very complicated software, and that requires a certain level of abstractions. And these days, we hear a lot that software development is dead. For example, recently Mark Cuban said software is dead because everything going to be customized to your unique utilization. What is your response or what is your view on this?
Well, I know Mark, and I don't think he's ever written a line of code himself. He's a marketing and sales guy. So, but he's entitled to his opinion. I don't agree with that. I think that it's not software development that's dead. I think that maybe coding gets replaced, but software engineering is even more important. And in fact, I'm always surprised that all these people says, oh, and it's true that some of the large software companies like Microsoft and Meta in particular have laid off a lot of people and all. But that's because they hired too many people. But a small company like us, who have some great developers who know exactly what they do and they are responsible and accountable for something meaningful. I haven't seen anybody thinking of not hiring more people because they're working on software engineering. The coding part is a small part of software engineering, whether you know how to put together a hash table or a bubble sort or whatever. That's that doesn't matter. It's the engineering part that's the important part, and that's, I think, something that humans are going to keep for a long time. It you could tell the machine invent a spreadsheet before the spreadsheet was invented, and it would have built something a little different and not something as clever as what we use today. Uh, but if you're thinking about an engineering problem, that's where I think humans and human competence is very important. Um, it's there's a side to this where um, when I hear statements like that, like some well-known CEO telling you there's not going to be any developers anymore. Don't go and learn computer science. I say no, learn twice as much computer science as you've done before, because it's going to be even more important. It's going to differentiate the thing. I'm talking about computer science. I'm not talking about go to 22.3 and that's not computer science. And uh, so I think that's really important, developing that organic intelligence. I call it organic intelligence as opposed to AI, our own intelligence. In other words, I was talking to a teenager the other day, and we're talking about chess. I'm not a very good chess player. I'm a mediocre chess player, but I like chess. And he goes, I play on chess.com and I have a very bad rating and blah, 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 but I really enjoy it. And um, he asked me, why do you do that? The machine is better than you are. I said, that is not the point. The point is making me better. Is and you know right now in China they have those robotic Olympic Games, whatever, and big news: the robot 26B XY whatever uh, ran the 100 meters faster than Usain Bolt. What? So what? I mean, of course that's going to happen, but that doesn't mean that we shouldn't run and that we shouldn't learn those skills. It's not because there are calculators that kids should not learn multiplication tables. They better. I mean, it's really, you know, I interview developers for what we do. We're very much into machine learning and stuff like that, and I'm always amazed by in an interview, I'll ask a simple question, uh, like, "What's an eigenvector?" Okay, says a what? Eigenvector. So why does that matter? I said, well, is linear algebra important to you as a practitioner of so-called AI? Well, yeah, but I've never heard of that. I said, that's the point. Is that you don't understand the underpinnings of what you do, and I think that's part of the engineering part is to have that broader understanding. So when people say those jobs would disappear and all that, I disagree with that. I completely disagree with that, and that's just as simple as that. Uh, you know, it's. I think there's going to be more, and kids should go more into computer science and learn more and dominate the subject.
Thank you. More questions, please. Okay, I will take advantage that we still have time, and can I ask you, in this community, for many years, we're trying to democratize the process of development of smart decision models. And basically, one of our major goals was to move business logic back to hands of business users, not software developers. But the best result is when they work together and everybody does their own parts. And these days, AI really brings us closer to this objective when business subject matter experts are in charge of business logic. Just few comments from you.
Yeah, I mean, it's you know, it's funny you bring that up because back in the late 80s, early 90s, we came up, my Borland days was something, I was very interested in rules-based system and AI at the time. Believe it or not, I'm a Lisp fan and still am. Uh, but at the time, we thought that a rule-based system that would be helpful would be Prolog. And so we actually brought up something called Turbo Prolog at the time, and I was very interested in that approach. And I think that that is the critical part is it's a little bit the same. It's a little bit what you're saying is that you're trying to orchestrate um, talented people who each bring something to the table to create a better um, a better environment for decision rule-based systems. I think that's what I hear in what you're saying.
Yeah. Yes. Yeah.
I do have a question.
Go ahead.
Sorry, this is James Lavelle.
Yeah,
Yeah, my question is, I know there's been a lot of development in the decision model notation and other graphics or notational systems from the semiotic and areas. So essentially leading up to model driven development. Do you believe that still has a place within the context of AI, and particularly with respect to distributed judgment and being able to model, overall interactions, particularly regulated interactions?
So I'm not an expert enough to answer that question intelligently. So I will defer it because I'm not sure up to date here. So I'm sorry, I'll choose not to respond to that because I don't think I'm an expert enough to answer that.
It's fair. Okay, last question, please. Okay, in this case, I just okay. Somebody.
No. I'll jump in once more. Sorry, Trevor Miles again.
Okay.
So, I just quickly, lots of the other speakers have talked about the adoption of AI, and often it is that it has to gain trust and all of this type of stuff. Jeffrey Moore, a few weeks ago, wrote a very interesting article talking about beta risk. And basically, this is the discussion we've been having today, where everybody focuses on the alpha risk, the mistake that a machine will make. Whereas the beta risk is the mistakes that humans make already, or that humans do not take, or take too late, or everything else like that. And that is never taken into consideration in that evaluation of value. That it's only ever what if the agent gets the decision incorrectly? And that's the key thing that people focus on. What's your take on this?
I think my take is kind of my slide on orchestrated agents, that the whole idea is not to have a bunch of agents chatting with each other, but have a regulated interaction with clearly defined roles and challenging uh, challenging assumptions as opposed to a system that never really truly challenges itself. So I think that my answer to that in a situation like that is really that level of orchestration, which is not, uh, bunch of agents chatting with each other. Again, it's a functional architecture that verifies at every step the next step and regulates the handover from one to the other, even if there's multiple handovers simultaneously, but it has to be regulated. And I think I totally agree. The machine is going to, make mistakes and et cetera. And so the only way we this works is if we're serious for that. And an example is a self-driving car. Is those mistakes are not reversible. If you have a system where the mistakes are reversible, it's not as important. You can, if you scramble a spreadsheet for your financials, well, you can build another spreadsheet. If you destroy the your wedding pictures, you'll never get new wedding pictures. If you that's mission critical. And so that requires checks and balances when you talk about copying files or duplicating things. And the same thing, a self-driving car in the real world is okay. Same thing with airplanes or whatever it is. It's not reversible. And at that point, yeah, I think you have to make choice to actually put in the checks and balances that come with a highly regulated, orchestrated system.
Okay. Okay, Philip, thank you very much for your presentation and for all you did before. And we all used your products, and all the best. Thank you.
Well, thank you so much, and great conference, and thank you for having me. It's always great to interact with people who make things happen.
Thank you, Philip.
Bye bye.